Hello students, this is the recording that goes over part 2 of the chemistry final exam. So taking a look at our next question, which will be question number 9, it's all about chemical formulas. So remember that chemical formulas are the way that we can abbreviate which elements are in a compound. Remember that there are little subscripts, which are small numbers down at the bottom, which help us to identify how many atoms there are of that element. Remember, it's a subscript after the abbreviation that tells you how many there are. If there's no subscript, that just means 1. Remember that a lot of times when we have blanks in our chemical formulas or in our equations, blanks mean 1. So taking a look here, you can see, for example, that H2O, the 2 comes after the H, and so that means there are 2 hydrogens, so 2 hydrogen atoms in this molecule. And then there again is a blank here. Remember, blanks actually mean 1, and so that means that there is 1 oxygen in this water, 1 oxygen atom. Okay, so let's go ahead and try this out with some practice problems, and then we'll go ahead and make sure to look at the exam question. So for example, in class we took a look at a couple different examples. Sulfur dioxide, SO2, so this capital S is its own element, and this capital O is its own element. And taking a look here, the capital S has no subscript after it. And remember, anytime we have a no subscript or a blank, that just means 1. So in this case, there's 1 sulfur. And right here, there's a 2 after the oxygen, so there must be 2 oxygens. Taking a look down at ethylene, again, this carbon is, the C is an element by itself, that's carbon. This H is an element by itself, that's hydrogen. So taking a look here, the 2 right here is attached to the C, and the 4 is attached to the H. So there are 2 carbons and 4 hydrogens. And then taking a look at this example over here, remember that each of these capitalized letters is a letter by itself, is an atom by itself. Remember that you can have atoms that have 2 letter abbreviations. Just remember that that second letter is going to be lowercase. So helium, for example. So if I had the number 7 following helium, then that would actually count for this entire part. So this is entirely an atom by itself. He is helium, as opposed to H, which is hydrogen. So taking a look here, all of these capitalized letters are their own elements though, so I would put a 1 after each of these, so C1, H3, C1, O1, O1, H1. Okay, so taking a look at carbons, you can see here that I actually have a carbon here, C1, and a carbon here, C1, and so 1 plus 1 would actually give me 2 carbons, so the answer here is 2. Taking a look at hydrogen, we can see there's a 3 following this hydrogen and a 1 following this hydrogen, so 3 plus 1 would actually give me 4, and again that comes from the 3 and the 1. And then finally the oxygens, I can see there's an oxygen right here with a blank, which is 1, an oxygen here followed by a blank, which is 1, so this 1 plus 1 tells me there are 2 oxygens here. Okay, so at this point, understanding this, you should be able to do the next question on your own. I'll go ahead and show you what it looks like. So you have a compound here with 3 different elements in here. So you can see here you have to take a look at the first element, second element, and third element and tell me how many there are. Again, if you have a number following it, so for example, if I'm saying X, Y, Z, all right, whatever number follows it, so if this is 1, 2, 3, except for remember that a 1 will actually be a blank. So taking a look here, blank, 2, 3, then you would know that this right here is a blank, so that actually means 1, right? This actually means 1. All right, this 2 following this would mean there were 2. And this 3 following this would mean that there are 3 Z's. So 1X, 2Y, 3 Z's. Again, this is just an example. Do not copy this. Example, do not copy. All right, so go ahead and pause the video and answer this question and then continue playing when you are ready. All right, so let's go ahead and talk a little bit about how to then take a chemical reaction, and we have big numbers in front of chemical reactions. So remember when we were taking a look at chemical formulas just a moment ago, we have little letters. Little letters tell you how many atoms are in the actual compound. This time though, we can use coefficients, which are big numbers that are going to go in front of each molecule, and that'll tell you how many molecules we need for that chemical reaction. Again, it's like the recipe card for our chemical reaction. So the goal of balancing equations is that on the left side, the individual amount of atoms on the left should be equal and balanced with the individual atoms on the right side. And so we need however many molecules of everything, every compound that we have, in order to make sure that the left side equals the right side. And this just goes back to conservation of matter, where you can't delete or add matter to the universe. Whatever you start with is also what you need to end with. Remember that if we don't have a coefficient, a big number in front, that just means 1, just like we talked about, blanks mean 1. Let's go ahead and take a look here. So you can see here that I have an unbalanced equation. H2 plus O2 reacts to give us H2O. So hydrogen and oxygen react to make water. Now each individual letter, again, is an abbreviation for an individual atom. So each abbreviation is a single atom, whereas each circle is a whole molecule. So for example, what that means is that H2 is the whole molecule, and in that whole molecule we have 2 hydrogen atoms, 1, 2. Same thing here, oxygen, O2, that's the whole molecule. Inside of oxygen, though, we actually have 2 oxygens. Again, H2, this is the whole molecule, but inside of that molecule we have 2 hydrogen atoms and 1 oxygen atom. So let's go ahead and take a look at what we're starting off with. So we can see here that on the left side we have 2 hydrogens, which I've labeled over here. You can see that we also have 2 oxygens on the reactant side. Remember, the left side is called the reactant side, the things that we start with in our recipe. Okay, now on the other side, we can see that we have 2 hydrogens, which I wrote over here, and 1 oxygen, which I wrote over here, and this is the product side. All right, and so taking a look here, the individual atoms, the individual abbreviations or letters here are not balanced, right? So the hydrogens are fine, but the oxygens are not. The way that we do this is that we are going to take a look at what side needs more. Okay, so currently, again, the hydrogens are fine, but the oxygens are not balanced. So I need to think about which side needs more. And that side, the right side, the product side, is the side that needs more oxygen. It only has 1 oxygen. Now, you can't just add a random oxygen over here because there is no oxygen on the right-hand side. You can't just add letter O's. You can only add more of the molecules you already have. And so the molecule I already have on the right side is a water. So I'm going to go ahead and add another water. So H, O. And so recounting the individual atoms, 1, 2, 3, 4, I now have 4 hydrogens. And recounting the individual oxygens, 1, 2. So now I have 2 individual oxygen atoms on the right. So now our oxygens are balanced, right? We have 2 oxygens on the left, 2 oxygens on the right, but our hydrogens are not. Now we have 2 on the left and 4 on the right. So again, I need to think about which side needs more. Taking a look here, obviously the left side, our reactant side, needs more. It only has 2. So taking a look here, again, I can't just start adding random H's here. I can only add more of what I have. So more of what I have is either going to be the H2 or the O2. So I'm going to add more of a molecule that contains the hydrogen that I actually need. And so that would only be H2. So I'm going to add another H2, H, and taking a look here and recounting, I have now 1, 2, 3, 4 H's, and still 1, 2 oxygens. So now looking on the left and on the right, we have 4 hydrogens, individual hydrogens, 2 oxygens, 2 individual oxygens on each side. And so now this equation is almost balanced. I've drawn out what we need. However, I do need to actually answer the question. So remember that these big molecules, these big circles or molecules, are going to become our coefficients. So the big circles molecules become the coefficients. The big coefficients in front in the equation. Okay, so taking a look here, you can see here that I have 1, 2 big circles or molecules, and so a big 2 should go in front of our H2, telling me that I need 2 big circles or molecules of H2. Taking a look here, you can see I only have 1 big circle of O2, and so I could put a 1 in front, but instead I'm just going to leave it blank because remember, right here, leave blank, because blanks mean 1. All right, so I'll just move that right there. Cool. Now this last one, let's take a look at H2 over here. So counting up the big circles of H2O, I have 1 big circle, 2 big circles. So I'm going to put a big 2 in front right here. And so now this is my balanced equation or recipe card. In order to have the correct number of hydrogens and oxygens on the left and right, I need 2 H2s plus 1 O2, which will result in 2 H2Os. Let's go ahead and take a look at one more example, and then you will need to be able to do the exam problem on your own. All right, so let's go ahead and talk a little bit about methane reacting with oxygen to form carbon dioxide right here and water here. It also forms heat in the form of fire, but we're not balancing the fire. Fire is not a chemical. All right, so let's go ahead and take a look here. I need to first go ahead and fill out what each of these molecules are. Remember, this goes back to my chemical formulas. So you can see CH4. There is no number after C, so this is going to be 1 carbon with 4 hydrogens. So in here, I'm going to go ahead and write CHHHH to show that's what CH4 looks like. That's its individual atoms. Again, we're going to start off, each abbreviation is a single atom, so CHHHH. All right, O2, we already learned there are 2 O's in O2, so O, O. And CO2, again, the C has a blank following it, so that counts as a 1. O2 obviously counts as 2 O's, so COO. And then finally, taking a look at H2O, we already know this, there are 2 hydrogens. There's a blank after oxygen, which counts as a 1. So right here, this is going to be 2 H's and an O, HHO. All right, so let's go ahead and then take a look here at what's going on each side. So taking a look here, I currently have 1 carbon, 1, 2, 3, 4 hydrogens, 1, 2 individual oxygen atoms, again on my reactant side. On my product side, taking a look here, I have 1 carbon, hydrogens, 1, 2 hydrogens, and 1, 2, and don't forget this third one over here, 3 oxygens. Okay, so let's go ahead and take a look at what needs to be balanced. So currently we have 1 carbon on the left, 1 carbon on the right, that's fine. We have 4 hydrogens on the left and 2 hydrogens on the right. That is not fine, we need to fix that. So I have 4 on the left, 2 on the right. That means my right side needs more. So again, we can't just add a random hydrogen over on the right side. You can only add more of what you have. You can only add additional big circles, big molecules. Okay, so taking a look here, the only circle here that contains hydrogen is a water molecule. So I'm going to go ahead and add another water molecule here. So I'll add another H, H, O. And taking a look here and recounting, you can now see that I have 1, 2, 3, 4 individual hydrogens in total on the right. And 1, 2, 3, 4 oxygens now on the right. Make sure you're careful with this because we did actually add another oxygen because again, you have to add an entire molecule, which in this case is water. Water also includes oxygen. So our carbons are now balanced and our hydrogens are now balanced. Let's take a look at the next thing. So oxygen only has 2 on the left. There are 4 individual oxygens on the right. So obviously we need to fix that. So the left side obviously needs more. So taking a look here, which of these 2 molecules would give me more oxygen? Because again, I can't add random oxygens. CH4 won't give me more oxygen, but O2 will. So I'll go ahead and add another O2 here. So O, O. And taking a look here, 1, 2, 3, 4, I now have 4 O's. And when I added this extra O2, it did not change the number of carbons or hydrogens. All right, so taking a look here, now my carbons are the same on both sides. My individual hydrogens are the same on both sides. And my individual oxygens are the same on both sides. However, I'm not finished. Now I need to actually balance the equation. So again, the way that we balance the equation is now we look at the big circles. So big circles or molecules become the coefficients, the big coefficients in front. Okay, so that's just a reminder. We already kind of talked about that. So let's go ahead and take a look here. So right here, I only have one big circle of CH4, so in front. I could put a 1, but again, I'm just going to leave it blank because blanks mean 1. Right here, I have two big circles of O2, so 1, 2. So I'll put a big 2 in front of O2. Right here, I have one big circle of CO2. Again, I'll just leave it blank because blanks mean 1. And finally, H2O, I have two big circles of H2O. And so in front of H2O, I'll put a big 2. All right, and so that will be our final answer for this example. Now, let's go ahead and take a look at the actual exam problem. All right, so in this chemical equation, everybody has a different chemical equation. They're also not real chemicals, so you can't just Google it. You have to actually try it on your own. But essentially, you have a compound that contains A, B, and C, which are imaginary compounds, and they result in two other compounds, something with A and B, or B and C, or an A by itself, or a C by itself, or so on and so forth. So you do need to go ahead and grab a piece of paper and draw it out for yourself. I recommend that the most. Make sure again that the letters end up the same on both sides, and then count up the big circles to find the coefficients. So balance the individual atoms, which are the letters, and then the coefficients will be the number of big circles molecules. Right, so the coefficients, that's what your answers actually are. So you should be filling in the coefficients here after you have balanced the individual letters, the individual atoms. So that's step 1. Here's step 2. Okay, pause the video and continue playing when you're ready. Again, make sure that you've practiced the previous problems. That way you know what to do with this one. Okay, so let's go ahead and take a look at the next question, which is all about molar mass. Atomic mass, on the periodic table, we have a mass that we've already learned about, and the mass is always on the bottom. Now, depending on if you're talking about an individual atom, this can be the mass of an individual atom in the units AMU, atomic mass units. So, for example, 12.001 AMUs is the mass of a single atom, and that comes from the protons plus the neutrons. Okay. On the other hand, you can actually also use the same number, and the same number is actually also the number for the molar mass. So 12.001 grams is the mass of 1 entire mole of carbon, which is something that you can actually see. So this is an amount you can actually see, because we know that a mole is the same as 6.02 times 10 to the 23rd atoms. So that's like 6 quadrillion something atoms. So it's enough atoms that you can actually see this amount. So anyways, when we talk about molar mass gets, the units for it is grams per mole. So grams in an entire mole. And again, it's still going to be the same number at the bottom that we already learned about is mass. So at this point, you should be able to do the next problem. Let's go ahead and take a look at this. So according to the diagram below, what is the molar mass of blank? And everybody, again, will have a different question. Again, molar mass is found at the bottom of the element's square, and is measured in the units grams per mole. All right, make sure that when you enter your units here, that again, it should be grams per mole. Okay, no spaces, sorry, I know that's a little confusing, but otherwise the computer will mark it wrong, so make sure that you write it correctly, grams per mole. All right, so you do need to include all of the digits, so make sure when you're looking at that bottom number, make sure you copy exactly what you see up here. Pause the video and continue playing when you're ready. Okay, so our next question is then going to ask, how do you calculate the molar mass of an entire compound? So previously we were looking at the molar mass of just a single element. Now we're taking a look at the molar mass of a compound, which is made up of more than one element. Okay, so in order to do this, all you need to do is take the molar mass of each of the individual elements that make up the compound and multiply it by the number of times that element is in that compound, which again we already learned is the subscript, that little number at the after each element. So taking a look here, we can then add up the results. So an example here, H2O, again we need to count up the number of hydrogens, which is the number after the hydrogen. So there's a number 2 after the hydrogen, so there are 2 hydrogens. And we're going to multiply it by its molar mass that we see on the periodic table in the lower part of the square. So taking a look here, so here is hydrogen. Oops, sorry. Here's hydrogen right here. And so the lower number right here is 1.008. All right, so I'm going to go ahead and fill in that the molar mass of an individual hydrogen is 1.008. Okay, but again, I actually have 2, so that's why we're multiplying it. 2 times 1.008 will give me the actual molar mass, and if I were to plug that into a calculator, I would get 2.016. I'll prove that to you. So 2 times 1.008, you would get 2.016. So overall, these 2 hydrogens actually give us a molar mass of 2.016 grams per mole. All right, that's not enough though. There's still an oxygen in this compound, so we also need to account for the oxygen's mass. And so the oxygen has a blank after it. Remember that blanks actually mean 1. All right, so there's 1 oxygen in here. So 1 times whatever the molar mass of a single oxygen is on the periodic table. Taking a look at oxygen, oxygen's mass at the bottom is 15.999. Again, units being grams per mole, so 15.999. Again, there's only one of them, so it's 15.999 times the 1, and so this equals 15.999 grams per mole. And now we have the molar mass of our 2 hydrogens, we have the molar mass of our 1 oxygen, and so we just put it all together by adding them together. So taking a look here, I'm going to go ahead and grab my calculator, and so I would be adding, let's see if I can put this up here. There we go, 2.016 plus my oxygens overall, which is 15.999. And so finally, I end up with a final overall molar mass of water being 18.015. Again, units are still grams per a single mole of water. So this means if you were to go into your kitchen scale, for example, kitchen scale, and measure 18.015 grams of water, which is like a tablespoon or something, this would be the same as a single mole of water, okay? Which again is 6.02 times 10 to the 23rd molecules of water. It's a lot of water atomically. All right, so let's go ahead and take a look at the next question at our actual, I can do another example here. So if you need more help, again, I'll just put these examples in. So CO2, there's no number after the C, that counts as 1, so 1 carbon. After the oxygen, there's a 2, so 2 oxygens. Again, I already know that the molar mass of oxygen is 15.999. The molar mass of carbon, though, going back to my periodic table, carbon is going to be 12.011. So 12.011. And I would multiply those together. So 12.011 times the 1 carbon is still going to be 12.011. The oxygens, there's actually 2 of them this time, so I actually need to take the 15.999 and multiply it by 2, and so I would get 31.998 grams per mole. Okay, and so now I know how much a single carbon weighs and how many 2 moles of oxygen weighs, and so now I just need to put it all together. So 12.011 plus 31.998. And I would get a final overall molar mass of carbon dioxide being 44.009 grams per mole. All right, now finally, let's take a look at this example of ammonia. So ammonia, again, there's no number after the letter N, so that counts as 1, so 1 nitrogen. There's a number 3 after the letter H, so 3 hydrogens. The molar mass of a single nitrogen, take a look at nitrogen, is 14.007. So right here, I would plug in 14.007, and again, there's only one of them, so it's still going to be 14.007 grams per mole. Whereas for hydrogen, there's 3 of them, so let's take a look at what an individual hydrogen is. Again, 1.008, but again, I have to multiply it by all 3 of them. So 3 times 1.008, so the 3 hydrogens all together end up being 3.024 grams per mole. And now I know how much a single mole of nitrogen weighs, and I know how many 3 moles of hydrogen weighs. So now I just need to put it all together. So 14.007 plus 3.024 should give us a final molar mass of 17.031 grams per mole of our overall compound here, which is ammonia, NH3. All right, so at this point you should be pretty familiar with how to do these, so now we can go ahead and take a look at the actual problem. All right, so you have a compound here that's made up of some amount of A, some amount of B, and some amount of C, and I have already provided the molar masses here. These are not real elements, these are just pretend elements. But again, what you're going to do is you're going to count up the number of A's, and the number of A's should go in here, right? So based on your compound right here, the number of A's, plug that in right there. And then the molar mass of A, which in this case, I'll go ahead and just tell you that. All right, because why not? Which in this case is 15.1 grams per mole. Oops, sorry, 15.1 grams per mole. So once you have the number of A's in your compound, multiply by 15.1, and that should give you the final amount of all of the A's. Same thing, put the number of B's here, put the number of C's here, and multiply them by their appropriate molar masses. You can see molar mass of B, molar mass of C, and that'll give you the total molar mass for B's. Oops, sorry, this should say the letter C. Total mass for letter C. And then finally, all you have to do is add them all up together. So take all of these answers, add them all up together, and that will give you your overall molar mass of this initial compound. Pause the video and continue playing when you're ready. Okay, so we now need to go ahead and take a look at a stoichiometry problem. It's a one-step stoichiometry problem. So remember that we learned a couple different ways that we can convert between different amounts or between different chemicals in a chemical equation. So we learned that if we have the molar mass of a compound, it allows us to convert between the mass and moles of that compound. If we are using Avogadro's number, which is that 1 mole equals 6.02 times 10 to the 23rd particles, that could mean molecules or atoms, then we can convert between particles and moles of a compound. However, you'll notice that molar mass and Avogadro's number can only be used for that actual same chemical, right? It can only be used, in this case, to go from pink to pink, or over here from blue to blue. Okay, the only way that you can actually get from one chemical to a different chemical is to use the magic mole ratio. And a mole ratio can be found by using a balanced chemical equation, because a balanced chemical equation, again, is a recipe that tells us how much of everything we need. And so what we can do is we can take a look at the coefficients, and based on that, it will help us figure out, based on how many we start with of one chemical, we would need to end up with this amount of the other chemical, or we would need this amount of chemical, etc., etc. So let's go ahead and take a look at this actually in action. So again, the only way to convert between different chemicals is to use the mole ratio. So let's take a look at an example of ethane and oxygen reacting together. So this right here is ethane, C2H6, and oxygen, O2, and when they react, they create CO2, carbon dioxide, and H2O, water. This is another example of a combustion reaction, which again means we're lighting things on fire. Okay? Now again, you can take a look at these big numbers in front. That tells you how many big molecules that you would need. So in a chemical reaction, I need 2 molecules of ethane plus 7 molecules of oxygen to give me 4 molecules of carbon dioxide and 6 molecules of H2O. But remember that molecules are really tiny. Molecules are really tiny, we can't see them, and they're not useful for real life reactions because it's too small of an amount. Okay, it's too small. So instead, we are going to use moles, but right, the cool thing about chemical reactions is they are also talking about moles. So instead of saying molecules, we can say moles. So 2 moles of ethane, all right, which is an amount that you can actually see. So now we have big amounts, all right, with 7 moles of oxygen will react to make 4 moles of carbon dioxide and 6 moles of water, which is like a cup of water. It's an amount, again, that we can actually see. All right, so instead of saying molecules, now we're going to say moles. So that being said, we can use these to make mole ratios, because for every 2 moles of ethane, I know I need 7 moles of oxygen, and you can write that as a fraction. So for every 2 moles of ethane, we need 7 moles of oxygen. So I'm just taking the coefficients and plugging them in. Coefficients and plugging them in. Okay, so this means per, right? Division signs here, sorry. Division signs mean per. All right, so for every 2 moles of ethane, there's 7 moles of O2, or 2 moles of ethane per 7 moles of oxygen. You can also reverse it, so you can also say for every 7 moles of O2, there are 2 moles of ethane. So again, 7 moles per of oxygen per 2 moles of ethane. And let's go ahead and take a look at how that actually helps us with one-step stoichiometry calculations. All right, so let's say that I want to know how to go from moles of one compound to moles of a different compound. So the question here is, how many moles of iron would you need to produce 20 moles of iron oxide, Fe2O3? Now we need to start off with what we know. That means what we actually have a number for. So taking a look here, the only actual number I have is 20, and so this is going to be my known. All right, so I'm going to start off with what I know, which is that I have 20 moles of iron oxide. So I'll go ahead and fill that in. My units are MOL, which is the abbreviation for moles, and the actual compound, Fe2O3. You do need to include the actual compound as well. So 20 moles of Fe2O3. And now I'm going to put it over the number 1 just to turn it into a fraction. Dividing by 1 doesn't change it. So that's just a nice, easy way to turn it into fractions, because fractions are a little bit easier to visualize when we do stoichiometry. All right, so now I'm going to go ahead and use my mole ratio, because we learned that mole ratios can allow us to get from one type of compound to a different type of compound. So moles of iron oxide to moles of just iron by itself. So the way that I need to do this is I want to get rid of these units right here. I want to get rid of moles of iron oxide. Now, in the next step, in order to get rid of it, I need to put it on the opposite side of the fraction, because when you have a number on the top and on the bottom of a fraction, it cancels out to 1, and that 1 can just disappear. You don't have to write out that 1. In the same way, when you have the same units on the top and the bottom, they cancel out to 1. So for example, if I have 3 divided by 3, that cancels out to 1. But if I have a dog divided by a dog, that also cancels out to 1. And again, we can just kind of disappear the ones. All right, so taking a look here, in order to get rid of moles of iron oxide, which is on the top in the first step, I need to put it on the bottom of the next step. Okay, now finally, that's going to get rid of those moles of iron oxide, but I do need to make sure that on top I have what I'm solving for. So taking a look here, the question is how many moles of iron? So the question here is, this is what I'm solving for, moles of iron. So again, MOL is the abbreviation for mole, and you must include the actual chemical name, Fe for iron. Okay, so plugging that in here. All right, now I'm going to go ahead and talk about where do we get the number for the mole ratio? Well, we just learned that. We learned mole ratios come from the chemical equation. All right, so taking a look here, I need a mole ratio where iron is on the top and iron oxide's on the bottom. So taking a look here, I'm going to use this top one right here. I don't need this bottom one right here. That would be if I flipped them. That would be if I was solving for iron oxide instead. All right, so again, the numbers though for the mole ratio come from the actual chemical equation. So I need to look at the coefficient of iron, which is 4. Right, so that gets plugged in right here because that's moles of iron. And for moles of iron oxide, which is over here, we look at its coefficient, which is the number 2. All right, so plugging this in into this equation, I would put 4 moles of iron oxide per 2 moles of iron oxide, 4 moles of iron per 2 moles of iron oxide in our chemical equation. That should allow me to convert based on what we started with. So I know I have 20 moles of iron oxide. I need for every 4 moles, 2 moles of iron oxide, and so 4 moles of iron, 2 moles of iron oxide, and so that will help me figure out finally how much iron would I actually need overall. Okay, so now we're going to go ahead and multiply these together. When you multiply fractions, you just need to multiply the numerators, the tops together. So 20 times 4. And you multiply the denominators together, the bottoms. So 1 times 2. And multiplying that together, 20 times 4 equals 80. And 1 times 2 equals 2. So now I'm left with this fraction, 80 over 2. But remember, fractions are just division in disguise. So what I can also do is now I can simplify this even further and just do 80 divided by 2, which gives me 40. Now don't forget your final units. Final units are the units that did not get canceled out, those units that we were solving for. And so in this case, this would be for moles of iron. All right, so go ahead and make sure you understand that problem because this will help you with your next exam problem. All right, so taking a look here, it says if you have blank moles of A, how many moles of B will be produced? So taking a look here, this is a number, so this is what you are starting with. This is your known, and so that is what you should be filling in first. Okay, so whatever this number is what you should be filling in first. And again, units here are MOL A, moles of A. You do need units, otherwise the computer, otherwise you will be marked as wrong. So put in your known moles of A. Again, it's already over 1 to turn it into a fraction. And the next step, now we need the mole ratio. Now to figure out the mole ratio, again, we want to get rid of moles of A on the top. So in the next step, we need to put it on the bottom. Moles of A on the bottom. And that will get rid of moles of A, right? So that'll eventually get rid of those. Okay, I'll show that again later. On the top though, what I'm solving for, again, the question here is moles of B. How many moles of B? So the units on the top here should be moles of B. So this is what our units for our mole ratio should look like, but now we need the actual numbers, and the actual numbers for mole ratio come from the balanced chemical equation, which is already provided for you. All right, so I already actually have that up here for you. Okay, so taking a look here, you need to look at what is the coefficient for B, moles of B, that should get plugged in here. And what is the coefficient for moles of A? That should get plugged in on the bottom. So again, start off with what you know. Everybody has a different amount of known. Make sure you then plug in the mole ratio. Everybody has the same equation, so your mole ratios should all look the same. Okay, then you're just going to multiply the tops together, multiply the bottoms together, so fill in blank times blank like you would on top, blank 1 times blank like you would on bottom. Solve that. What do you get on the top? What do you get on the bottom? And then go ahead and divide. Remember, it's the top divided by the bottom to get your final answer down here. Now again, remember that moles of A get canceled out and you should end up with moles of B. So that's the question here, was how many moles of B? So your units, your final units here must be moles of B. If you don't include units, you will be marked down. So you do need to include units in the first step and in the answer. Go ahead, pause the video and continue playing when you're ready. Okay, so now we're going to go ahead and talk about our most recent unit, which was acids and bases. So remember that an acid is a compound that contains hydrogen, and when it is dissolved in water, those hydrogens get donated into solution as positive hydrogen ions or cations. Okay, so anytime we have an acid, that means positive hydrogen cations or H pluses. Okay, now the difference between a strong acid and a weak acid is not necessarily how much they can injure you. Strong acids, if you add enough water, won't hurt you, and weak acids can, if you make them concentrated enough, can hurt you. But strong acids, weak acids is actually talking about how well they dissociate or separate into their separate ions in water. So for example, hydrochloric acid is a strong acid. And the reason hydrochloric acid is a strong acid is because when it goes into water, it completely separates into its positive hydrogen cations, plus the other stuff, which in this case, the other stuff would be negative chlorines. But again, the positive hydrogen part tells you that that is the acid. It's definitely an acid. Weak acids, on the other hand, do not completely dissociate. For an example here of a strong acid, you can see up here, none of the original chemicals left over. So none of the original chemical is left over. Okay, so none of the original chemical left over. Weak acids, on the other hand, do not dissociate completely. So they do dissociate some, they do release some hydrogens. So for example, you can see hydrofluoric acid releases some hydrogens, indicating that it's definitely an acid. It also releases some of the other ion, which in this case is fluorine. But some of the original hydrofluoric acid, it still exists in its non-dissociated form, so it still exists as its original HF. You can see another example up here of carbonic acid. Carbonic acid, some of those carbonic acids are still there. H2CO3s have not actually dissociated. So they do have the acid part, the H+, and the other part, which is HCO3-, but they also have some of the original chemical still there. So the original, some original is still left over. So that's the difference between strong and weak. Let's go ahead and take a look at strong and weak bases, which are very similar, but bases, when dissolved, actually cause OHs, OH negatives, to increase. So these are what we call hydroxide ions, and so negative hydroxide anions mean negative, so AH negatives, that tells you it's a base. Okay, please note that not all bases actually themselves contain hydroxide. A lot of them do, but some actually force the water to form the hydroxide for them, still making it basic because hydroxide ions still increase when they are placed into solution, but they're actually forming that hydroxide by forcing the water to make it for them. But again, there are many of them that do actually contain hydroxide. So an example would be sodium hydroxide, which is made up of Na and OH. And this is a base because when it's dissolved in water, it releases the OH negatives, those hydroxide anions. That's the indicator that it's definitely a base. And it releases the other stuff, which in this case, the other stuff would be a sodium positive cation. Okay, so let's go ahead and take a look at weak and strong bases. Again, these have to just do with dissociation. Again, a strong base doesn't necessarily have to hurt you if it's dilute enough, but a strong base is defined as completely dissociating in water. So taking a look here, sodium hydroxide completely breaks apart into those OH minuses, the hydroxide anions, plus the other part, which in this case is sodium. Okay, so you can see that right here. There's, again, none of the original left over. So none of the original NaOH is still in solution. Now, a weak base, on the other hand, does not dissociate in water. The example we talked about in class is ammonia. Ammonia exists as a mix of the hydroxide ions, which again tell us that it's a base. Okay, it must be a base if it's releasing hydroxide ions. It also exists as the other part of the ion, which is NH4+, and some of the original. So again, some of this original is still here. You can actually see some of those originals are still here. Okay, so this means some original is left over. Okay, now again, this is just a quick note that ammonia itself does not contain hydroxide, but when it is dissolved in water, it forces water to release the hydroxide for it. The way that it does that is it steals one of those hydrogens, and when you steal a hydrogen, which is H from water, which is H2O, when you steal a hydrogen and pull that off, you're left with an OH, and that's where that hydroxide comes from. So it is still a base because hydroxide is being formed. Even though the ammonia itself doesn't have it, it's forcing water to form it. All right, so that should help you with the next question here. So you have a compound. It tells you whether or not it dissociates completely or not completely, and it indicates what the ions are. So remember that acids will have H+, hydrogen ions, hydrogen cations. Bases will have OH negatives, which are negative hydroxide anions. Remember, if it dissociates completely and none of the original is left over, then that makes it strong, whether it's a strong acid because it's releasing H+, or a strong base because it's releasing OH-. And if it does not dissociate completely, and some of the original is left over, that makes it a weak acid or base. Okay, so everybody has a different chemical and a different description, so make sure you read that carefully to figure out, first, is it an acid? Second, is it first, is it an acid or a base? And second, then is it weak or strong? Pause the video and continue playing when you're ready. All right, so let's go ahead and talk about how we can determine the different types of acids and bases. So remember that we have a pH scale, and pH scale tells us how acidic or how basic a substance is. So the more you get towards the red side, remember red means acidic. The more you get towards the red side, that is going to be the most acidic, the most extreme. So 0 and 1, for example, are very very acidic pHs. The more you get to the blue side, B for blue, B for base, the more basic it will be. So taking a look here at 13, 14, those will be very basic. And in the center you have neutral, neutral being 7. Okay, so 0 is going to be the most acidic. So this is going to be what we call highly acidic. That's things that can actually like burn your hands. 14 is also going to be highly basic, which can actually also burn you and hurt you. Once you get to these like 4, 5, and 6 range, these ones become only slightly acidic, right? These are things that we can actually like eat if they're not toxic, right? So tomato juice is slightly acidic, but we can actually eat it, right? It's not going to burn a hole through our esophagus. And over here, this is slightly basic. Slightly basic. Okay, so 8, 9, and 10 will be slightly basic. And again, in the center, we have neutral, which is just pure water. Okay, let's go ahead and take a look then at the actual question. So everybody will have a different pH strip color. So all you need to do is kind of match it up with what you see on our pH scale here. If for some reason you can't see these colors, just ask someone to help, or you can always contact me and I'm happy to help as well. Okay, so again, taking a look here, we know that the more towards the left you are, the more acidic. So highly acidic is going to be the like 0, 1, 2, 3 range. Slightly acidic will be the 4, 5, and 6 range. Sorry, let me make that a little bit more condensed. So 4, 5, and 6. And then the slightly basic will be 8, 9, and 10. And the more highly basics will be over here towards the right, like 11, 12, 13, 14. Okay, and then in the center we have neutral, right? So neutral is right in the center. Okay, so based on that, you should be able to determine the pH strip. Is it showing a highly acidic pH, slightly acidic, highly basic, or slightly basic pH? Pause the video, continue playing when you're ready. All right, so the last question is asking about calculating a titration. Remember that a titration is the way for us to determine the concentration or molarity of an unknown solution by neutralizing it with a known solution. Since we're talking about neutralization, it has to be an acid with a base. So our known solution, we know its identity, we know if it's an acid or a base, we know how much of it we have, and its concentration or molarity. The molarity is the way that we measure concentration of an acid or a base. The unknown solution, we know a lot about it too. We know what it is, its chemical identity. We know that it's the opposite. So if we start off with an acid, then the unknown should be a base. If we start off with a base, then the unknown should be an acid. We know how much gets added during the titration, and specifically we want to reach neutralization. And from there, we can calculate the one thing that we don't know, which is the molarity or concentration of that unknown solution. So unknown is kind of a misnomer. We know a lot about it, we just don't know its concentration or molarity. Now, again, the only way that my equation for a titration works is if the if it's at its neutralization point. So that means that we need to know when neutralization occurs, and we can use an indicator called phenolphthalein to know when neutralization occurs, because when we have a acidic solution, phenolphthalein is clear. When we have a basic solution, it is bright pink, but when we have a neutral solution, it is faint pink. And so if we add acid to base or base to acid, once it reaches the faint pink point, we know that it's at a neutral point, and now I can use the special titration equation to calculate the molarity of the unknown solution. So taking a look here, this is what this kind of looks like. So we did this in class. So in class we filled up our bottom right here with an acid. Which in this case I think is HCl. And at the top we filled with a base, which I think in this case is NaOH. Okay. So for this bottom part, we actually will know the exact amount. So we will have 25 milliliters of our acid, and we also will know its molarity, which everybody has a different one, so I'm just going to put in that you know the molarity of the acid. Now up here, we do not know the molarity of the base. That's unknown, and that's what we are actually going to end up calculating with our special equation once this is neutralized. And once it's neutralized, you can actually look at this pipette right here, and you'll know the total volume that was needed to neutralize this. So what we did in class was we added a bunch of drops until finally this turned light pink because there was phenolphthalein in it. So again, there was an indicator in it, phenolphthalein. So once this turns light pink equals neutralization. Okay, and so at that point we measured how much of this we had, and so this becomes known. So it becomes known the amount that we have, and once we know how much we need to turn it neutral, we can then calculate our unknown molarity. So let's go ahead and take a look at the question here. So it says that you know that you have blank milliliters of hydrochloric acid that has a concentration of blank molar. To neutralize the hydrochloric acid as shown by the phenolphthalein indicator in the solution turning light pink, the titration required blank milliliters of NaOH. And the question is, what is the unknown concentration of NaOH? Remember, we have an equation here that the molarity of the acid times the volume of the acid is equal to the molarity of the base times the volume of the base, only at neutralization, which is why we needed the phenolphthalein to turn light pink. Okay, now taking a look here, HCl, you should know, is our acid. So hydrochloric, this is our acid. And so you should be putting your molarity and volume of your acid on the left. If you are not putting them in the right spot, you will not get full points. You do need to follow the equation here. Now, molarity is going to be the molar part. So whatever number you have here of your acid, molarity should go into this blank. And the volume is measured in milliliters. So volume here is measured in milliliters. Again, you have to make sure that you are putting them in the correct blanks. Otherwise, it is not clear that you understand what the units are representing, or what thing is your acid, or what thing is your base. So in this case, the milliliters of hydrochloric acid should go under volume. And then finally, the unknown concentration of our sodium hydroxide, that's our base. So sodium hydroxide is our base. So everything for the base should go on the left side. So, sorry, HCl stuff should go on the left, and NaOH stuff should go on the right. Okay, so taking a look here, the molarity of our base is what we're solving for, the molarity of our NaOH. So that I just leave as a variable. And the volume of our base, we actually figured out by doing the titration. So that's our milliliters. That needs to get plugged in for volume of our base. Sorry, let's see. I'll just put it right here. Okay. So once you have your molarity of your acid and your base, again, you can write those down here. You can then multiply them together to simplify. So you should simplify the left side. Simplify the left side by multiplying. Okay, so multiply these two together using a calculator, and that answer goes in here. Okay. For this part, just pull down this number. All right, this should be the same number. Same number, because you can't yet simplify it. Then what you should be able to do is you should be able to do an algebra problem. So whatever you multiply over here on the right side, you need to get rid of this, and the way that you do that is you divide by it, because division is the inverse. So right here you would divide, okay, by this number on the right, right? But whatever you do to one side, you also need to do on the same on the other side. So on the other side, I would also need to divide by the number from the right. Divide by number from the right side. Okay? So again, it should be the same number. You divide by this number on the right, and you divide by that same number on the left. Okay, but again, this was your original number that you simplified from here. Okay, once you divide that, you take the top part divided by the bottom part, and that should give you your final molarity. Go ahead, pause the video, and then make sure that you fill this in correctly. You do need the correct answers in each blank to get full credit, and continue playing when you're ready. All right, that's everything you need, and I will talk to you later.